Hi, hello. Now that we know the mathematical expression for the gravitational force between any two objects of masses m and m at a distance r, we can calculate what is the gravitational force between the Earth and you and me. First thing we need to notice is that this force, just like any other force, follows Newton's laws. In particular, it follows Newton's third law. This means that the force that the Earth exerts on the Moon is the same as the force exerted by the Moon on the Earth, but in opposite direction. Look at the equation. The negative sign indicates that it is an attractive force, but the unit vector points in the direction from the object feeling the force to the object exerting the force. So, for the force that the Moon experiences because of the Earth, this force points towards the Earth, while the force experienced by the Earth points towards the Moon. Of course, this force obeys Newton's second law also. If an object experiences this gravitational force, it will experience an acceleration equal to this force divided by its mass. This is, for example, what keeps the Moon in orbit about the Earth. Or better said, the Moon and the Earth orbit about a common center of mass. Let us now calculate the force of gravity that you and I experienced due to the gravitational force between the Earth and us. Because the vector of gravitational force points from the object, one object to another, we can consider it as from the center of mass of one object, you, to the center of mass of the other object, the Earth. This means that the gravitational force field points radially from the surface, where people usually are, to the center of the Earth. We can use this expression to write the mass of the Earth, and my mass, for example. R will be the radius of the Earth. Now let me do it for your mass. Now let's use it for Doctor Who. And we could continue with any person, animal, plant, object, whatever. If we look at these equations, they are similar. They all share g times the mass of the Earth divided by the radius of the Earth squared. Then that common thing is multiplied by our mass. If we remember from a few chapters ago, the gravitational force experienced by any object on the surface of the Earth is also known as weight, equal to mg, where g is the acceleration of gravity on the surface of the Earth. So we rename this constant as lowercase g, and we check the numbers. G is 9.8 meters per second squared, and is a characteristic of the planet given by its mass and its radius, if we are near the surface of the Earth, of course. Newton's universal law of gravity can be simplified as force is equal to mass times g. If you go to another planet, the acceleration of gravity on its surface will depend on its mass and its radius. But if you go away from the Earth, let's say, for example, to the International Space Station, the gravitational acceleration at that distance of 400 kilometers is reduced. You should not confuse the fact that the astronauts at the ISS are weightless. That is because they are in free fall in orbit around the Earth. But if the station was at rest at that distance, if it was not orbiting, then they would experience a reduced acceleration, a reduced g. The mass of the Earth does not change, but the distance is larger than the radius of the Earth. Remember that we already saw that if you are in free fall, imagine that you are inside a lift that breaks and freely falls, then you would be weightless inside the lift, as you and the lift will be accelerating at the same rate, g. For the Moon, we have that its mass is 7.35 times 10 to the 22 kilograms. Its radius is 1,737 kilometers. This gives us an acceleration of gravity on its surface of 1.62 meters per second squared. One thing you could do now is calculate the mass of the Sun using Newton's universal law of gravity, and then calculate the acceleration of gravity that the Earth experiences due to the Sun. For that, remember that the Earth takes 1 year to make one revolution about the Sun, and the average distance between the Sun and the Earth is 150 million kilometers. May science be with you.